Okay, this is work that I've done jointly with David Whitaker, who's a colleague of mine at the University of Waikato, and Triggs, who's at the University of Auckland. And what I want to try and do is to give you a flavour of what we're doing by looking just at a simple example. Okay, here's a very simple incomplete block design for 10 treatments and 15 blocks of 4 and 6 replicates of each treatment. So I'm taking the sort of equal block size, equal replicate case. From the design we can get the incidence matrix, and the incidence matrix here has got 10 rows corresponding to the 10 treatments and 15 columns corresponding to the 15 blocks. So the one here represents that treatment is in a block 0, but it's not in a block. We note a few things about that incidence matrix. The elements are 0 and 1, so that the treatment is either in a block or not in the block. So we have what's called a binary design. Each treatment will occur 6 times, so that in terms of this incidence matrix, the row sums must be 6, and then there'll be 4 treatments in each block, so that the column sums will be equal to 4. Optimality criteria, well, we look at based on the non-zero eigenvalues of the matrix, which I call C. It's a little bit different from the C matrices we've seen before. In fact, this is 1 over R times the information matrix. If we denote those non-zero eigenvalues by E1 up to EV minus 1, then something like A optimality is to choose the design to maximize the harmonic mean of these eigenvalues. In other words, we minimize the sum of the EI's to minus 1. Sometimes that's not convenient because it requires eigenvalue calculations. So there are various approximations around which really involve looking at the sum of the EI to the power m, the nth powers of these eigenvalues, and minimize them, or some function of them. So if you put m equal to 1, that's just a constant. M equal to 2, you get ms optimality and so on. The advantage here, of course, is that you can work with traces of matrices rather than with eigenvalues. So we can think of the problem of constructing block designs as a mathematical program, that what we require to do is to minimize some function of the eigenvalues subject to a number of side constraints in terms of the row sums being equal to R, column sums being equal to K, and the fact that these Nij's are 0 or 1. And so since this particular function we've got here is a nonlinear function of the elements of the incidence matrix, we see that C is essentially just a function of the incidence matrix N. Then our objective function is a nonlinear objective function in these variables Nij. So we have a nonlinear integer program which we have to solve. The size of the problem in the example I've got, N is a 10 by 15 matrix. So we've got 150 variables, 0, 1 variables, and I've got a total of 25 constraints. In general, we'll have VB variables and V plus B constraints. So in general, it's going to be a very large problem. It's a feasible problem to solve. We've tried using standard nonlinear integer programming packages. We use minus with various sort of adjustments, and it's possible to get results, but it does take time on the computer. So what we thought we'd do is to look to see if we can simplify the problem or make the problem more feasible by looking at classes of design which had some very high degree of structure. And this led us to look at cyclic designs. Okay, in fact I can rearrange the design I gave you at the beginning in this particular form, and that's a cyclic design. What we have here is that the blocks are generated from previous blocks by just adding 1 modulo 10, and from that we can write down the incidence matrix, and that incidence matrix has a high degree of structure. You can see, for example, if I put it like that the columns of that incidence matrix can be generated cyclically from those that I've marked, the 2 columns that I've marked here. And the blocks corresponding to these 2 columns that I've marked are called initial blocks. I notice the second mark column generates just 5 other columns instead of the full cycle of 10 columns, and that's known as a half set. Now I've taken these 2 columns as the ones to generate the other columns, but in fact I could have taken any 2 columns, any column here or any column there, and those columns would have done equally well. So there are in fact other pairs of columns that could have been chosen. We've got 10 here, 5 there. So there's a total of 50 possible pairs of columns, all leading to exactly the same design. Now what this means in terms of programming the integer program is that we've got lots of feasible solutions that are identical. And although we could sort of get a computer algorithm to churn through all these feasible solutions, it's a waste of time to do this. We need some way of homing in on just perhaps one of those rather than the 50 possibilities. Because most integer programming algorithms are in fact complete searches through feasible solutions, and we need to be able to speed that up. Now, one other little thing to notice about this half set is that the matrix that I've got in the continuous box there is identical to the matrix I've got in the dotted box. And what we're getting from this half set is really that it's a duplication of some smaller design. And so when you look at partial sets, you can, instead of looking at designs with 10 treatments, it essentially comes down to looking at designs with 5 treatments. So although I talked about the full columns, in fact I only need to consider the full column of one set and half the column on the other set. So the size of the problem in this particular case is now down from 150 0-1 variables to 15 0-1 variables, and in general for cyclic designs the total number of variables will be just the number of blocks. The number of constraints will be the number of cyclic sets we've got. Again, there's lots to program this and to get it so that it works quickly. There are lots of little tricks that we use. The most important perhaps is to try and cut down these 50 feasible solutions to just 1 or 2. And this really comes to the choice of an initial block. Now, one obvious thing to do is to constrain the choice of an initial block to have treatment 0 in it, or have one of the treatments. I'll take the first treatment, treatment 0. And if I do that, then the only columns having 1 in the first row, which is what treatment 0 is 1, 2, 3, 4, 4 in here. Oops, I think this is over 1 too many. Okay, 1, 2, 3, 4 in the first one, and 2 in the second one. So 4 times 2 gives us 8 possibilities. So immediately, by defining my initial block to contain treatment 0, I've reduced the number of feasible solutions that I have to search from 50 down to 8. I can in fact take it a stage further, and what I can do is to divide up these columns into 2 sets. The sort of top set here and the bottom set, in both the full sets and in the half sets. So I can split the rows into 2 halves, and then you'll find that in the full set only one of the 4 candidate columns, in other words 1, 2, 3, 4, only one of the 4 candidate columns has 2 1s in the top half and 2 1s in the bottom half. And in fact it's this column here. You can see a 1, 2 and a 1, 2. In the half set only one column has a 1, 1 split, and it's this one. There's a 1 there and a 1 there. And what this means is that if you split the rows in this particular way, then the number of possible feasible solutions that you've got has been reduced not only from 50 to 8, but from 8 to 1. It does mean that the number of constraints increases from 2 to 4, but when you're programming an integer problem, the number of constraints doesn't matter, because you're only programming feasible solutions. Now, we've proven that in fact you can generate all possible cyclic designs by splitting up the initial blocks in this particular way. So that's one device we've used to speed up the algorithm. There are other devices. I don't have time to describe those. Let me just tell you a little bit about the performance of the algorithm. First of all, just a comment about the efficiency factors and the concurrence matrix N prime. For a cyclic design, that particular concurrence matrix is a circulant, and so when we look at that, we only really need to look at the first row of that matrix. In other words, we look at the concurrences of the first treatment, which is treatment 0, with the other treatments in that first row. So you'll find that there are 2 4s there, there are 3 2s, and 4 1s and no 3s. And you can, by looking at these distribution of concurrences, you can say a lot about the optimality of the design. So a better design, for example, might be this one, which has sort of less spread in these concurrences and therefore would be a better design. Another nice little property of cyclic designs is that because the concurrence matrix is circulant, you can get the eigenvalues of that matrix in terms of the roots of unity, and this means you can get a closed form expression for the canonical efficiency factors, and that clearly makes it much easier to program than having to use eigenvalue routines. Okay, well, the performance of the algorithm, we've tested out the algorithm against all known, well, the main tables of designs. The tables by myself, Wallach and Herb David, 1972, and another set of extensive tables by Lammercraft and Hall in 1982. And we can generate all the designs in those tables very quickly, and we can produce designs which are at least as good as those tabulated, and in some cases better. I found quite a few designs which are better than the ones in my catalogue. Of course, the advantage of an algorithm is that it can go beyond the tables, and we've in fact designed an experiment, or used these to design an experiment in forestry, where we had 130 varieties in blocks of 30. I won't go into arguments about whether that's a suitable design to use. I think perhaps we should have, a resolvable design should have been used, perhaps rather than one of these cyclic designs. But something like this doesn't take long on the computer to produce a design which, not necessarily optimal, but certainly close to being optimal. Let me just finish by showing you one little device which I think is quite useful, not just in cyclic designs and in integer programming, but perhaps in general construction of designs, and that is to use the sequential method of construction. Now, I can't give you any theoretical justification for this. It just seems intuitively obvious that something like this might work, and certainly my experience of using this suggests that that's the case. Just to show what I mean, suppose I want to construct a design with 38 treatments in blocks of size 8, and I've got 124 replicates. Now, in terms of a cyclic design, that means 3 full cyclic sets, each cyclic set producing 8 replicates. Now, I can run the algorithm with those parameters, and if I sit there patiently, eventually, and it does take quite a few minutes, eventually I'll get this particular design out. It's got a concurrence distribution like that, an efficiency factor which is 99.94% of the upper bound. And you might think, well, surely that's good enough. Remember that these average efficiency factors are averages, and you need to look at the distribution of these efficiencies. What this means is that some of the treatment contrasts are estimated with fairly low precision compared with other treatment contrasts. And what I would like, if I'm designing an experiment, is to try and get these sort of distributions much closer together. They're just a bit too far spread out for my liking, even though that might indicate that it's quite good. Now, I guess if you run this algorithm for a few hours, you'd improve this, but I'll suggest perhaps a quicker way of doing it. And that is this, that what you do is you build up the design one cyclic set at a time. So we run the algorithm, just taking a single cyclic set with R equal to 8, and instantly you'll get this particular design of that particular initial block, which is a nice, efficient initial block. We then input that particular initial block into the next stage. So step 2, we add another cyclic set. We fix the first initial block to be that, and then we run the program to pick up the second initial block. And then finally, at the third step, we'll add in another cyclic set where I use those two as my initial blocks. And then I'm really just trying to find a third initial block. And we find this almost instantly, which has concurrences which are much nicer, much closer together. In fact, that's what's called an MS optimal design. A balancing complete block design just doesn't work here. The upper bound is pretty close to 1. So this sort of approach we found quite effective, and that example with 130 varieties, we used a sequential approach and got a very good design very quickly. The final transparency, just a comment on dual designs. When V is greater than B, then cyclic designs are known to be relatively inefficient. And this is because of that repeating pattern I had. Remember I said that the continuous block was exactly the same as the dotted, continuous box was exactly the same as the dotted box. And when you get these sort of half sets and quarter sets or partial sets, that results in some sort of inefficiency in the design. And in this situation, it's much better to switch to the dual design, switching blocks and treatments. And we allow that in the program. So a little example here, if you want a design with 10 treatments, a half set, the best cyclic designs got this as an efficiency factor. If you switch to the dual, done by interchanging blocks and treatments, then the cyclic design is this one, which is a balancing complete block design. And therefore we know that as we switch back again to our original design, that this design will be A-optimal. When you switch back from a cyclic design to a dual, you don't necessarily end up with a cyclic design. And in this particular case, it's not a cyclic design, it's known as in this example, as a generalized cyclic design, which you get by adding 2 to each element in the initial block. So this is an algorithm that we've developed. It's fast, we get pretty good results. If anybody wants to see it, I've got a copy here, we can play with it on a computer, we can find it down later.
Thank you, Professor John. Any questions at this, Professor John?
So algorithm give you efficiency bounds or guaranteed efficiency, or you may have to use other inputs to compute the efficiency of the solution which you get.
Are you talking about some upper bounds?
Yes, you said that your algorithm, you're looking among cyclic design, and this may not be the optimal design.
Okay, yeah.
Designs of relatively high efficiency.
Right. We have upper bounds in there, which will tell us whether the design is a good design or not, compared with the upper bound.
But the upper bound has nothing to do with the algorithm, or you get the upper bound from the algorithm.
The upper bound is a theoretical upper bound that's in the literature. Now there are cases where the cyclic designs are not efficient. A lot of cases where they are, but there are a few cases where they're not. And you need perhaps to go to some other program, perhaps just to tighten it up. And I've very effectively used Hui's program to do this. So I can take my cyclic design as a phase 1 design, which I can put into Hui's algorithm, and I can tighten up these if the design isn't efficient. And I find that particular approach is very useful, because the comment I can make on Hui's algorithm is that the phase 1 can be very slow, and if you input a cyclic design, you can sort of tighten up on some of these things.
Just one more comment on efficiency. In general, dual of a VIP design is optimal only in the equi-replicate class.
Right.
Not in general. I mean, not in the whole class.
No, we're just looking at equal replicate designs.
I think there are no more questions. We thank Professor John for a very interesting talk.